today's lecture we will see another approach to solve the production planning problem, and this approach is based on dynamic programming. Let us consider this problem that we have shown here. Again, let us assume that we make a single product and we have the demand for 4 periods or 4 months given as 80, 60, 40 and 70. There is a setup cost that is incurred whenever there is production. For example, if we choose to produce in the first month, then in addition to the cost of production, there is a cost of setup which is say rupees 60. So, the setup costs are given as 60, 40, 60 and 45. There is also a cost of production which is given as 5, 4, 5 and 5. In addition, there is an inventory cost, which means one can produce in say month 1 and use the production to meet the demand of month 2. If we do such a thing, then we incur a certain inventory cost or inventory holding cost. We are also going to assume that the inventory cost of 2, 2, 1 and 2 represent the cost of holding the ending inventory at the end of this period. For example, if we choose to produce 100 in the first month and consume 80, the remaining 20 is assumed to be carried from the first month to the second month, and it attracts an inventory cost of 2, which is the inventory carrying cost at the end of month 1. So, these costs represent the inventory carrying at the end of each month. There is also a production cost, which is the cost required or cost that is incurred in producing these quantities. At the moment, we do not have an upper limit on how much we produce. For example, if it is economical and profitable, one can produce, the total demand is 180 plus 70, 250. So, if it is economical and profitable, one can produce all the 250 in the first month itself. There is no limit on the production capacity at the moment. As we move along, we will also realize that it is not very difficult to incorporate a production capacity if it is there. So, there are 3 costs that are involved: the cost of setting up, the cost of production and the cost of holding inventory. In our problem, we have also assumed that these setup costs are different in different periods, inventory costs are different in different periods, and production costs are also different in different periods. So, the decision or the planning decision is to find out how much is to be produced in these 4 months, in each of the 4 months, such that the total cost of setup, total cost of inventory and production, the 3 costs put together, is minimized. So, it is a minimization problem to minimize the cost of setup, inventory and production. Right now, we are not bringing time into consideration. We have not explicitly modeled the time taken to produce these items and the capacity that is available in terms of time. One should also note that the setup cost 60 also involves a setup time, and since we are not explicitly modeling the time, we do not bring the effect of setup time into the analysis. But if there is a production in a certain month, a certain amount of setup cost is incurred if we decide to produce in this month. This model is slightly different from the earlier models that we have seen, the tabular approach, the linear programming approach and the transportation approach. The difference comes from the fact that for the first time we are including a setup cost. Previous models that we discussed did not include setup cost explicitly. This model includes setup cost explicitly. We also said that whenever we decide to produce in a particular month, we have to incur the setup cost. for the purpose of modeling we are assuming a single product whose demands are so much. We also assume that if it is decided to produce in months 1 as well as in month 2, we will incur a setup cost of 60 in month 1 and 40 in month 2. We are not assuming that once it is set up it is going to remain the same for all the 4 months. Every month if there is a production there is going to be a setup. One may also say that this facility can be used to produce more items and products, and therefore if this particular product is made in month 1 as well as in month 2, then we incur 2 setup costs, one for each month. The problem can be formulated and solved as an integer programming problem with of course a binary variable that would say that yi equal to 1 if we decide to produce in month I, and yi equal to 0 if we do not produce anything in month I. And we can have constraints that relate the decision to produce, which is the yi, and xi, which are the quantities that are produced in this month. So integer programming, binary integer programming is definitely a methodology to solve this problem. We also observe that dynamic programming is also a very good methodology to solve this problem, where the stage will correspond to each of these 4 months. The state variable for dynamic programming would correspond to the inventory that is available at the beginning of each period. Also note that this problem does not have an initial inventory, there is no product that is available, there is no desired ending inventory. So we do not wish to have any ending inventory at the end of this period. There is no beginning inventory as well as there is no ending inventory in this particular example that we are seeing. So if we use dynamic programming to solve this particular problem, then the state variable will be the amount of inventory that is available at the beginning of each period. The decision variable will be the quantity that is produced in each period, and the criterion of effectiveness or the objective function will be to minimize the sum of the setup costs, inventory costs and production costs. Now we all know that dynamic programming, though very useful to solve certain classes of problems, has its own issues with respect to modeling. So if we consider a problem of this type, the state variable can take very large numbers. For example, total demand for the 4 periods is 250. So if we use the tabular approach of dynamic programming to solve this, the state variable, which is the amount of inventory available, can take very large number of values, and the tables can become lengthy and cumbersome, though dynamic programming can be used to solve this. One of the most interesting simplifications to the dynamic programming solution came from Wagner and Witten, and it is called the Wagner and Witten algorithm, which uses dynamic programming to solve this particular problem. The Wagner-Witten idea or principle is as follows. Now there are 4 periods, and we are going to assume that we are going to make decisions on production at the beginning of each of these 4 periods. Now it is only logical that if we produce in a certain period, then we will have to meet the demand of that period at least. Otherwise we will have to incur one more setup and one more setup cost. Therefore it is uneconomical to consider 2 setups in a particular period. So if there is only going to be one setup in a particular period, then it implies that what we produce, we should be able to meet the demand of the entire period. One other assumption, important assumption, is that the demands have to be met at the beginning of each of these periods. Shortages and back orders are not allowed in this particular model. So under that assumption, if we produce something in a month, then either the quantity that is produced should be at least the demand of that month, or with the beginning inventory and production in that month, we should be able to meet the entire demand of that month. So, if there is a beginning inventory in the beginning of a particular month, let us say we are looking at month number 2, and let us say if there is a beginning inventory of say 20 in the beginning of month 2, then we should produce 40 or more. But then it is also logical to say that if there is a beginning inventory at the inventory at the beginning of this month, then if that inventory is sufficiently large to meet the demand of this month, then there is no need to set up and produce in this month. So, Wagner and Witten algorithm works around these ideas. So, there are two important points there. One is there will be production in a particular month only when the beginning inventory is 0. And if there is production in a particular month, then that production quantity will be the demand of that month, or the demand of that month and the next month, and the demand of 3 consecutive months, or the production quantity is always equal to the demands of certain number of consecutive months. The second, if there is beginning inventory in a month, then that inventory should be sufficient to meet the demand of that month, and there will be no production in that month. So, these are the two important results of Wagner and Witten, which I once again repeat. If the beginning inventory is 0, or only when the beginning inventory is 0, we will decide to produce in that month, and if we produce the production quantity is equal to the demand of that month, or the demand of 2 months, or demand of 3 months, or demand of a certain integral number of months. If there is beginning inventory, then we will not produce, and that beginning inventory should be sufficient to meet the demand of this particular month. The moment we accept and use these two results that came from Wagner and Witten, the dynamic programming solution to this problem becomes extremely simple. Now, we will look at how to solve this using dynamic programming under the assumption that back ordering is not allowed. So, let us go back and use the DP solution, dynamic programming solution. So, let us start with trying to meet the demand of month 1. So, we first look at trying to meet the demand of month 1. There is no beginning inventory, so we have to produce in month 1. So, demand of month 1 is met only in one way, by deciding to produce. So, we produce the cost equal to production quantity is equal to 80, because demand is 80, and the best way to meet this 80 is given by total cost is equal to setup cost is 60, which is to be incurred, production cost is 5. So, 5 into 80 equal to 460. There is no inventory that is carried, because demand is 80, production is also 80. There is only one way to do it, which is the optimal way. So, we just put a star indicating that this is the best way to produce and meet the demand of the first month. Now, we go to demand of month 2. Now, the month 2 demand can be met in two ways. One is to try and meet the first month's demand in the most economical way and use the previous result, which is the essence of dynamic programming, where the optimal decision up to the previous stage is computed and used for decision making in the next stage. So, one is to try and meet the month 1's demand in the best possible way, which is 460, which comes from here plus produce what is required for month 2 by incurring a setup cost of 40 plus production quantity is equal to, this is Q equal to 60, TC is equal to this. In fact, we do not even write this Q equal to, we just write TC, total cost is equal to total cost of meeting the second month's demand as well as the first month's demand, 2 months demand, is to meet the first month's demand in the best possible way, which is 460, that comes from here, and then meet the second month's demand alone by incurring a setup cost of 40 and a production cost of 60 into 4, 240. So this gives a total cost of 240 plus 40 is 280, 340 plus 400, 740 is the cost that is associated with this solution. The other way to meet month 1 and 2 demand is to produce everything in the beginning of the first month. So that would give us Q equal to, but it is produced in the first month. So all the 140 units are produced in the first month. So there is a setup cost of 60 that is incurred. All the 140 units are produced in the first month. So 140 into 5, $700 plus these 60 units are carried from first month to second month, and therefore there is an inventory carrying cost of this 60 into this 2. This 2 represents the cost of carrying 1 unit of inventory at the end of the first month to the second month. So 60 into this 2 is 120. So this becomes 700, 820 plus 60 is 880. Now the demand of months 1 and 2 put together can be met in 2 ways, one which gives us a cost of 740, the other that gives us a cost of 880, and since we are trying to minimize, 740 is the best way to do this. Now we go to month 3. Now month 3 can be met in 3 ways. One is to meet month 1 in the best possible way and then produce for 2 and 3 in month 2. The other is to meet month 2 in the best possible way and produce for month 3 in month 3, and the third is to produce everything in the first month and carry for months 2 and 3. So we have 3 ways of doing it. So let us assume the first way is we produce everything in the first month and then we carry, which means there is a setup cost of 60 . The total quantity produced is 60, 80 plus 60, 140 plus 40, 180, 180 into 5, which is 900, plus 100 units are carried at the end of the first month. So 100 into 2, plus another 40 units are carried at the end of the second month. So plus 40 into 2. So this gives us a total cost of 900 plus 200 is 1100, 1180 plus 60 is 1240. Second way to do it is to produce the first month's demand in the best possible way, which is 460, and produce the demands of months 2 and 3 in the second month. So, in the second month we incur a setup cost of 40, we produce the demands of months 2 and 3 which is 60 plus 40 100 in the second month. So, 100 into 4 400 plus, now this 100 is produced in the second month, but 40 is carried to the third month. So, there is an inventory cost of 40 into 2. Now, this gives us a total cost of 100 into 4 400, 480, 520, 580 plus 400 is 980. The third way to do this is by producing the demand of months 1 and 2 in the most optimal manner, which is by incurring the 740 and producing the demand of month 3 in the third month. So, this is to incur the 740 and then produce the demand of the third month in the third month by incurring a setup cost of 60, quantity produced is 40, production cost is 5, 40 into 5. There is no inventory cost here because this 40 is produced in the third month and it is not carried. So, total cost here is 40 into 5 200, 260, 300 plus 700 is 1000. So, the best way to do it is here. Now, we go to month 4. Now, we compute the total cost for month 4 in 4 ways. One is to produce all of these in the first month itself and carry. The second is to produce up to this optimally and then produce the rest here. The third is to produce up to this optimally and produce the rest here, and the fourth is to do up to this optimally and produce this. So, we will compute the cost for all of them. So, the first one will be to have all 4. So, produce 80 plus 60 140 180 250. So, TC1 first way to do it is to produce all the 250 in the first month itself by incurring a setup cost of 60, production cost of 250 into 5, unit production cost is 5, totally 250 are produced. Now, out of the 250, 170 is carried to the second month. So, 170 into 2 plus 2 into 170 plus 110 are carried to the third month, 110 into 2 plus another 70 is carried to the fourth month. So, out of the 110, 40 is consumed, 70 is carried, 70 into 1 plus 70, and this gives us a total cost of 1250 plus 340 is 1590. 1590 plus 220 is 1810, 1880, 1940. Now, we look at the second one where we do up to month 1 optimally. So, you incur 460 and we produce this 2, 3 and 4 in month 2. So, production quantity is 170 into production cost is 4. So, plus 170 into 4 plus out of the 170 60 is consumed here. So, 110 is carried, 110 into 2 . Now, out of the 110 that is carried, 40 is consumed, 70 is goes to the fourth period. So, 70 into carrying cost of 1, 70, and this gives us a total cost of, this is 680, 740, 1140, 1160, 1260, 1330. So, the total cost is 1330. Let me repeat, 170 into 4 is 680, 740, 1140, 1260, 1360, 1430. Let me do it again. 460 plus 680, 680, 740, 1140, 1000 plus 220 is 1360 plus 70 is 1430. Setup. So, I have to include the setup time also. So, there is a setup cost of 40 which comes here. So, that 40 has to come here. So, let me do it again from the beginning. So, the 460 is carried from here. There is a setup cost of 40 for this period. So, there is a setup cost of 40. The production quantity is 170 and the cost is 4. So, plus 170 into 4 plus out of the 170, 60 is consumed, 110 is carried, 110 into 2 plus out of the 110 that is brought here, 40 is consumed, 70 is carried, 70 into carrying cost of 1 is 70. Now, the total is 460 plus 40 is 500, 500 plus 680 is 1180, 1180 plus 220 is 1400, 1470. That is the total cost associated with this. I mean, the third way of calculating it, we produce up to this optimally, incurring a cost of 740, and then we choose to produce these two in period 3. So, it is 740 plus there is a setup cost, there is a setup cost of 60. So, plus 60, there is a production quantity of 110, production cost is 5. So, 110 into 5 plus out of these 110, 40 is consumed, 70 is carried, 70 into 1 is 70. So, this is 740 plus 60 is 800, 800 plus 550 is 1350 plus 70 is 1420. Then the fourth one, we produce up to this optimally and produce the requirement of month 4 in 4. So, the optimal way is 980 from here plus there is a setup cost of 45, there is a production quantity of 70 and production cost is 5 plus 70 into 5. There is no inventory involved. So, 980 plus 350 is 1330 plus 45 is 1375, which is the optimal one for this. So, out of these 4, the cheapest is 1375. So, what are the production quantities? The minimum cost is 1375. What are the production quantities? Now, the production quantity here in the fourth one, production quantity is 70. So, we will now say Q4 is equal to 70. So, when Q4 is 70, it means we are producing 70 here, which means we have used up to the third period, we have used the optimal solution. So, we have used this 980, which we see has also come here. Now, go back to this 980 and find out the production quantity, which is 100 into 4. 100 is the production quantity. So, that 100 comes from 60 plus 40. So, Q2 is 100. Let me explain how I got that 100. Now, the moment we are here, we are going to see the production quantity for at this point. This is the production quantity, 100 into 4 is the production cost. So, 100 is the production quantity. So, I am somewhere here, up to this I have solved optimally, and I realize that my production quantity is 100, which means I am producing here 60 plus 40. So, Q2 is 100. So, we have written Q2 equal to 100, and you also realize that 460 comes here. Indirectly, you also realize that here I have produced 100. So, I have to look at the optimization here, which happens at this point, production quantity is 80. So, Q1 is equal to 80. Now, total cost is equal to 1375. All right. So, we have now solved this optimally using dynamic programming. Now, there are 4 periods. The optimal solution does not ask you to produce in all of the 4 periods. It is enough to produce here, it is enough to produce here, and it is enough to produce here. In some sense, it is understandable because the production quantity comes down here. So, there will be a tendency to push the next month's production into this month. Pushing this might involve a higher inventory holding cost. So, it is a trade off between inventory holding cost and additional changeover or setup cost. But if the production costs themselves change, then this will also have a bearing on the solution. Now, in order to bring out the features of the algorithm, we have considered a problem where the inventory holding costs are different in different periods, production costs are different in different periods, and setup costs are also different in different periods. Though one cannot exclude this from happening, which means in organizations we will realize at some point when these costs are measured, one would realize that to set up for the same product, the setup cost can vary in different months. The reason could be many. Sometimes even the labor associated with the setup, the cost can change depending on pay revision and additional payments made to the people, and therefore setup costs can change. Inventory costs can also change due to many reasons. For example, if inventory space is added in a certain period or space is removed from the storage area, then there can be a situation where the inventory cost can change. Production costs can also change due to cost of labor and multiple other costs of consumable and so on. So, these things can actually happen, but this model is also applicable when the production costs are the same, the inventory costs are the same, and the setup costs are the same across all periods. There it becomes a trade off between cost of holding an additional inventory for a particular period versus the cost of incurring one setup or one changeover. The point I am making is, if all these costs are the same like 60, if all these costs are the same 2, all these costs are the same say 5, then it is a trade off between incurring a setup of 60 and carrying a certain quantity of the demand for the next period, multiplying it by 2. Wherever it is cheaper, then we would choose to set up, or we would choose to produce early and carry the inventory. So, the Wagner-Witten algorithm actually has become, once we apply the Wagner-Witten idea into the dynamic programming, we realize that it has become extremely simple. All we have done is, for 4 periods, we have just evaluated 4 plus 3 plus 2 plus 1, which is 10 possible scenarios. Whereas, if we had not applied the Wagner-Witten idea and done using dynamic programming, then for example, the state variable can take any value from 0 to 250, and therefore, we would have evaluated many more scenarios than we actually have evaluated. So, the Wagner-Witten idea has helped in the dynamic programming solution to this problem. Then comes the next question: do we allow back ordering into the Wagner-Witten solution? So, we also address the back order problem. The problem gets a little more involved when we consider back order. So, for example, how can we consider back order? See, right here we said that, see here, when we did not allow back ordering, there was no beginning inventory. So, the demand of the first month has to be met in the first month itself. So, we did not consider a situation where the first month's demand was actually met out of producing 140 here. If back ordering were allowed, then such a possibility exists. I do not produce anything here. Right now, when we did not consider back ordering, this model will definitely have Q1 equal to something, because the first month's demand has to be met at the end of the first month, and there is no beginning inventory. But in the back order case, we could actually have considered the scenario where we do not produce anything here, we make 140 here to meet these two, and maybe we could have considered another scenario where we make 110 here to consider these two. Or we could even consider a scenario of producing 180 here, meet a backlog of 80, meet this month 60, and meet the next month 40 here and a 70 here. So, considering back ordering throws open lot more scenarios than we can think of. But then we also have to include a back order cost. So, let us not spend too much time evaluating all possible scenarios, but let us try and understand one or two scenarios. So, let us include a back order cost which comes here. Now, let us consider the back order cost as 1, 2, 1 and 2. So, I am going to write the back order cost as 1, 2, 1 and 2, and this quantity is back order cost is shown here. For example, if I choose to produce 140 here, which means this period is back ordered, so the back order cost will be 60 into this 1, which is 60. Now, as I said, it throws open several scenarios. So, let us just look at one scenario that involves back ordering, and let us try and find out the cost. So, let us look at a scenario of 0, 180, 0, 70. It means I am going to produce 80 plus 60 plus 40, 180 here, which means I am back ordering this demand, I am meeting this demand in the month itself, and I am carrying to meet this demand, and then the fourth one that comes here. So, if we do such a thing, now what is our cost? So, now I am incurring a setup cost of 40. So, total cost will be setup cost of 40. I produce 180 here, the unit production cost is 4, the unit production cost is 4. So, 180 into 4. Now, out of this production, this 80 I am actually back ordering, first period 80 I am back ordering. So, let us say my back order cost is 80 into 1. This 60 I am meeting in the period itself, this 40 I am carrying to the next period. So, the inventory cost is 40 into 2. So, inventory cost is 40 into 2 plus the fourth period I am going to produce 70 here, I incur a setup cost of 45, I incur a production cost of 70 into 5, there is neither inventory nor back ordering. So, it is 45 plus 70 into 5. So, plus 45 plus 70 into 5. This is 720 plus 350 is 1070, 1070 plus 80 is 1150, 1150 plus 80 is 1230, 1270 and 1315. So, this is the total cost when we consider back ordering in this case. Please note, so far we have not solved the problem optimally, we have just illustrated a possible solution that includes back order cost, and we are able to show that if we include back ordering, then the cost comes down from the optimum 1375 to at least 1315, because 1315 is a feasible solution considering back ordering. So, back ordering is advantageous from a cost optimization sense, which is also understandable because when we solved this problem optimally, saying that there is going to be no back ordering, which was one of the assumptions, which means we have restricted the normal problem that could include back ordering, and we had solved a restricted version of a minimization problem. So, a restricted version of the minimization problem will only have an optimum solution higher. Now, this is a relaxed version. So, this optimum solution will be 1315 or lower. So, we can actually solve the problem optimally using the Wagner-Witten ideas by modifying it by saying that if my inventory is 0, I may even skip this period and back order it to the next period, that is the only modification. But if I have an inventory, I will not skip and back order, because I am incurring both inventory cost and back order cost, I will not do that. So, if there is 0 inventory, I need not produce in this period, I may still skip production and add it to back ordering. Now, for the same problem, if we consider back ordering, we have to evaluate more scenarios than we actually have evaluated. In this case, there are only 10 scenarios, but the case with back ordering has more scenarios than we actually have. Month 1, we incur cost equal to setup cost of 60 plus we produce the demand of 80 of month 1, incurring a production cost of 5. So, plus 80 into 5 would give us 460 as the cost for month 1. Now, we move to month 2. Now, we can meet the demands of month 2 in multiple ways. So, we could do 80/60, which means we produce 80 in the first month and 60 in the second. We could do 140/0 and we could also do 0/140. So, this gives us a cost equal to 740. 140/0 would give us a cost equal to 880 and 0/140 would give us a cost equal to 680. So, let me explain the computation of this cost, because this involves back ordering. So, we produce all the 140 in the second month and we meet the demand of 80 of the first month and 60 of the second. So, cost to produce this 140, there is a setup cost of 40 plus there is a production cost of 140 into 4 plus this 80 of the first month is back ordered. So, the back order cost for the demand of the first period is 1. So, plus 80 into 1. So, this would give us 40 plus 560, which is 600, plus 80, which is 680. So, out of these possibilities, this seems to be the best one, and this is the one that involves back ordering. So, with this we move to month 3. Where we can look at several combinations for month 3. So, we could use 180/0/0, we could use 80/100/0, 80/0/100, 0/140/40, 0/180/0 and 0/0/180. So, let us look at finding out the cost in two such instances. So, we will show the computation. For 180/0/0 the cost is 1240, for 80/100/0 it is 980. So, let us explain the computation in detail for a couple of instances. Now, when we say it is 180/0/0, it means in this case we produce 180 in the first month, consume the demand of 80 and then carry over 100 to the next month, and then consume the demand of 60 and carry over the remaining 40 to the third month. Now, let us illustrate the computation for two instances. Let us do it for this instance as well as this instance. Now, here is an instance where we produce 180 in the second month to meet the demands of the 3 months, which means there is a back order here as well as there is an inventory carrying here. In this scenario, we are assuming we produce the total demand of 180 in the third month. So, there is no inventory carrying, but there is back order, but back order for 2 periods. So, let us first show the computation for this. So, TC for this. So, let me illustrate this with some kind of a plus sign here. So, TC for the plus sign will be, I produce 180 here in the second month. So, setup cost is 40 plus production cost is 180 into 4 plus the first period demand of 80 is back ordered. The cost of back ordering the demand of the first period is 1, so plus 80 into 1. Now here we back order 80, we consume 60 for this period, so the balance 40 is carried over from second month to third month. So inventory at the end of period 2 is 2, so 40 is the quantity carried into cost, which is equal to 2. So this gives us a cost of 40 plus 720, 760 plus 80, 840 plus 80 equal to 920, which is what we find here. Now let us show the computation for this one. Let me illustrate this with 2 pluses just to show that we are looking at this computation. Here, as I mentioned earlier, there is no inventory, but there is back ordering. So the production is done in the third period by incurring a setup cost of 60 plus production cost is 180 into 5 plus the demand for both the periods are back ordered. So for this period the demand is 80, per period back order cost is 1, it is back ordered for 2 periods, therefore it is 80 into 2 plus another 60 demand for this period is also back ordered. Now back order cost per period for month 2 is 2, therefore plus 60 into 2. We should note the difference in the way we compute the inventory cost as well as the way we compute back order cost. In this particular example, when we did this 180 0 0, if I were to calculate the total cost here, now out of this 180 that is produced in the first month, 80 is consumed, so 100 is carried at the end of the first month. So 100 into inventory cost of 2 plus another 40 is carried at the end of the second month, so 40 into 2. So when we do the inventory calculation, we take the inventory at the end of that month and then multiply by the inventory cost at the given for that period. When we do the back order calculation, we go back here and say that the first period demand of 80 is back ordered for 2 periods. Now per period back ordering cost for the first period demand is 1, therefore 80 into 2 into 1, 1 is the cost, 2 is the number of periods. Here similarly 60 is the quantity back ordered, it is back ordered for 1 period with a cost of 2, so 60 into 2. So this gives us 60 plus 900, 960, 960 plus 160 is 1120, 1120 plus 120 is 1240. Now out of these we realize that this is the one with minimum cost. Then we move to month 4. Now with month 4 we work out several combinations and these are shown here. So we could do 250, 0, 0, 0, which is 1940, 0, 250, 0, 0, 1410, 0, 0, 250, 0, 1660 and 0, 0, 0, 250, which is 1815. 80, 170, 0, 0, which is 1470, 80, 0, 170, 0, which is 1560, 80, 0, 0, 170, 1635, 0, 140, 110, 0, 1360, 0, 140, 0, 110, 1315, 0, 140, 40, 1, 3, 3, 5, 0, 180, 0, 70, 1, 3, 1. So, these are the various solutions which we evaluate here. We also realize that these 4 are the situations where all the 250 is produced in a single month, and these 3 cases involve back ordering, because from here we back order this demand, from here we do both, from here all the 3 are being back ordered. Now, when we do this back ordering, the cost computation will be this 80 demand is back ordered for 3 time periods, the cost of back order is 1. So, this will be 80 into 1. Here it will be 60 into 2 into 2, because the 60 demand is back ordered for 2 periods, the cost of back order in that period is 2. So, this will become 60 into 2 into 2, and in this one it will become 40 into 1, because the other 40 is back ordered for 1 period, the cost is also 1. So, that when added with the setup cost of 45 and production cost of 350 would give us 1815. So, these 4 look at the cases where all the demands are produced in a single period. Now, here what we do is we have this 80 and then the 3 cases. So, if we look at this, for month 1 we have 80, which is the first one, the remaining 3 are now produced in 3 possible ways, including back ordering. There is back ordering here, there is back ordering here. Now, we move to the second month and we realize that the best value is 0, 140. So, we take the 0, 140 and look at the other cases that are here with 1335, and the third one, the best case is 0, 180. So, we have 0, 180, 0, 70. 0, 180, 0 gives us this 920 plus 70. Now, we realize that the best value happens in 2 instances, which is 1315 here, which also happens to be the solution here that we showed, compared to 1375 of the earlier one. This is the solution without back ordering. And these are solutions with back order. So, the 1315 that we calculated here and showed as a feasible solution is actually optimal to the case with back order. So, this is how we work out and solve the production planning problem using dynamic programming. Now, there are 3 important things which we have to look at before we wind up this discussion on the dynamic programming model. The first and foremost is this model is different from the earlier models, because here we have considered the effect of setup. In the tabular method, in the linear programming based method, and in the transportation based method, we did not consider setup costs. Now, dynamic programming gives us the opportunity to consider setup costs. The Wagner and Witten assumption has made the solution much simpler. When we did not consider back ordering, we looked only at 10 cases. When we considered back ordering, we did look at more cases. I have not gone to the detail of calculation of each of these numbers, but these are not difficult, considering that I have shown how each of these numbers are calculated, and also considering how I have shown how one particular thing is calculated. So, one can calculate all these costs and then find out. The number of calculations has increased. It is a little more than even double the thing that we have here, which means if we are looking at n periods, then this is roughly 1 plus 2 plus 3 up to n, and that would go about 2 to 3 times that number. Still, the number is actually small and manageable, because the Wagner and Witten method allows us certain conditions that we can use to solve this problem optimally. Then there are two other issues that we have to look at. One is, should we really consider back ordering? What is the impact of back ordering? What is the effect of back ordering from a practical point of view? One is, for the purpose of illustration, I have used that back ordering costs here 1, 2, 1 and 2 are kind of comparable to the inventory costs of 2, 2, 1 and 2. In fact, in this particular numerical illustration, I have even used values that are smaller than this, but in reality cost of back order is much higher than cost of holding inventory. Cost of back ordering has an important component, which is the loss of customer goodwill, because back ordering is employed. So, which is not a cost that can be easily measured. So, cost of back ordering is much higher. Many times back ordering also results in, for example, airlifting a certain product from one place to another place, because there is a delay and already there is one period backlog that is accumulated. So, people would like to transport it as quickly as possible with increased costs. So, cost of back ordering is much higher than cost of holding the inventory. So, should back ordering be planned? Many times the answer is no, because it is not very good to plan back ordering. But unless there is a requirement and there are certain demands which can actually be back ordered and not met, which simply means the customer is ready to postpone it because the customer has inventory already in the system, then in such circumstances back ordering may be permitted or considered. The third part is, we assume that the demand, all the 250 could be produced in a certain period. Many times there are capacity restrictions and we will not be able to produce all the 250. So, there can be restrictions on the maximum production that can be made in a particular period. Now, in the next lecture we will look at some more aspects of aggregate production planning. We will look at a couple of more models and one more model and a couple of other issues, after which we will move from aggregate planning to materials management or inventory control.